Now I'll discuss the implementation of part B. The reference to the code I followed is given in the first cell. This part is just importing the libraries. Next we load the images. So this function is written to load the images from the directory. Then we use the load function to load the images. This would take a while, around a minute. While this is running, I would explain the next part of the code. This is basically creating NumPy arrays of benign train labels, malignant train labels, and the test and their respective test labels. Also, we convert the benign and the malignant to categorical form, the labels to categorical form, that is 0 for benign and 1 for malignant. We also shuffle the data here. So once this is done running, we can execute the next part of the code. I'll wait for this to execute. Yeah, it is done loading. Now we can execute the next part of the code. So it just created the NumPy arrays. This part of the code is just visualizes the data set. The images that are there in the data set shows the sample benign and malignant images. I'll run this. It's running now. And it shows the sample malignant and the benign images in the data set. Next, we are generating the model. So basically, in this part of the code, we are defining the batch size, that is the number of training samples, and it is defined as 16 here. And the next is image data generator. This is done for data augmentation to increase the diversity of data. I'll run this. So, and this part of the data is building the model. As we can see that there is sequential here. It is just importing the convolutional models, and then we can add the layers to models. So backbone is the model that is specified here is added. Then we add the pooling layers, and also we set the dropout to 50%, 0.5, and then we add batch normalization and dense layers. Also, we compile the model with Adam optimizer. Adam optimizer, basically any optimizer, it just updates the weights or the hyperparameters based on the loss function here. So it checks the loss and it updates the hyperparameters. So I'll execute this. The next part is the 4 models that I discussed in the slides are executed here. The first is DenseNet 201. We use the weights from the ImageNet and we build the model with the summary. This will take a while. While this is running, I would explain the next part of the code. Reduce LR on plateau. It is just adjusting the learning rate based on the parameters. For example, here the patience equal to 5 represents that if the value of validation accuracy here is, it is set to monitor. If this does not change for 5 number of epochs, then we reduce the learning rate by a factor of 2%. And here we define the file to which we have to save the model. So basically we are just saving the best model here, setting the best save best only as true. So we see that the model is executed here. We can see the model summary. It shows the output shape and the parameters. Similarly, this model is trained for 20 epochs, as we can see here. So running this model is not feasible in this video because it takes around 5 to 6 hours to train a single model. So I ran it and I got the accuracies, and I've shown the results in the project proposal. And these are the values that the values were stored in the history parameter and here, and these are the values that I got, and this graph here shows the accuracy and the loss. So the first plot shows the loss, the training loss and the validation loss, and the second part shows the validation accuracy and the training accuracy. The values of all these are given in the slides. I'll jump onto the slides after this. Next, we set up the VGG16 model. I can run this, but this is again 20 epochs. So we're just setting up the model here. Just the build model is the function that we used earlier. We are passing VGG16 here. So the reference code just implemented the DenseNet model here. I applied the same to three different models here. VGG16 is one of them. Next, we plot the accuracies and the loss of every epoch for VGG16 as well here. And here we define VGG19 and we build the model and test it on the testing data set. We plot the accuracies and the loss for the same here. And next we have is the residual network 50, which is again tested and trained for 20 epochs. And here is a graph showing the validation loss, validation accuracy, and the training and the testing loss and accuracy. Now I'll jump back to the slide. So the results after running all those four models were DenseNet 201 achieved an accuracy of 92.54%, while VGG16 achieved an accuracy of 85.04%, which is quite less amongst all the models. And similarly for VGG19 it is 85.85%, and for residual network it is 90.26%. So the conclusion here is that for the part A of the implementation, kernel SVM RBF performed the best amongst all the models. It showed an accuracy of 97.5% on the testing dataset, while DenseNet 201 resulted in an accuracy of 92.5% on the test dataset, and thus it shows the best accuracy amongst all the models. While in the part A of the implementation, the link I followed, it classified random forest as the best model, but I trained it using the k-fold cross-validation technique. And in part B, the experiment was just performed on DenseNet by the reference code, but I compared all the four models. So lastly, I would just like to say that a critical step in the battle against cancer is early diagnosis. It also exposes many treatment options if the cancer is diagnosed early, and it also increases the survival rate. And I think this can be achieved with the use of sophisticated machine learning technologies like deep learning models and AI. So I think we can explore a lot more in the field of AI and machine learning to enhance the process of cancer detection, be it any type of cancer. This project dealt with breast cancer detection. Thank you.